That's gonna be okay.
No?
Ah, yeah. Oh, okay, let's get started. So we talked about system of the bosons. Like cesium or rubidium or nitrogen atoms. I mean sodium atoms, which have some repulsive interaction. The Hamiltonian as a collection of individual atoms with this repulsive interaction, and we have demonstrated that this Hamiltonian for the point particle is the same as the theory of quantum field theory. This is the action of the quantum field theory, right? And then talked about the fact that this actually shows something very, very surprising, namely that when you go to a very cold temperature, when the wave functions of individual atoms start to overlap, namely the interparticle is smaller than the thermal wavelength. And you're looking at the sum of the thermal wavelength. Thermal wavelength is meant to be the 2 pro E wavelength. Where this momentum is meant to be the thermal average. And you look in the homework problem what the temperature should be for the atoms to overlap with each other. So when this happens, then the atoms, the gas, start to behave like a classical wave. So that's what we talked about. We talked about experimental evidence that that indeed does happen. And we have seen the fringe pattern between two flows of cold gas. And you see this fringe pattern. And this classical wave is different from the probability wave. Where you have to keep doing the same experiment over and over again to see the fringe pattern like this one, because it's probability wave. But in this case, you see this fringe pattern on one shot, on a single measurement. That is different from the matter wave we have studied in quantum mechanics for the Schrödinger equation. So this fringe pattern is something you see on one shot of the experiment. You see these two flows of the cold gas. You shine light on it, then you see this variation in densities on one shot. And that's why this is meant to be really a classical wave instead of a probability wave. And we argue that it's of course not completely classical because it's highly quantum state of matter. This is something what should be called a semi-classical. So that is what we talked about based on this idea of the quantum field theory. So this is the problem. you can solve in quantum mechanics. This is the correlated state of matter. You have this interaction going on. You don't know how to solve the ground state for the problem. But in QFT, it turns out that solving for the ground state turns out to be the same thing. Just looking for the Euler-Lagrange equation for this quantum field theory as if it were classical field theory. And all you have to do is to solve the Euler-Lagrange equation and that gave us this that gives a tool to understand this experimental data. So that's what we discussed so far. And what I told you last time is that this is actually a very unusual kind of gas because it flows without viscosity. So that's one thing I haven't explained yet, and that's what I would like to explain today. So that's the first thing we will talk about. Then after that, we go actually into discussion of the fermions. But before doing so, are there any questions about what we discussed last week? Especially now that you're working on a homework problem round. Any questions? Yes?
You can talk about excitations from the ground state. I saw there were slides from last time.
I couldn't hear.
Excitations about the ground state. Are you going to talk about them? There were slides from
Why that's the ground state?
no, excitations.
Oh yeah, I will talk about that. Yeah. So, any other questions? Okay. So the question is, why is this a superfluid? Namely, no viscosity. So when you talk about, for some friction or viscosity or dissipation, you're talking about daily experience. That if you, for example, if you go to the bowling alley, you let the bowling ball roll, then of course it keeps going for a while, but it starts to slow down. And that's the friction, right? So what is going on there? So if you have, for example, maybe the simplest analog is that if you have a ball in a swimming pool, and then if you actually let the ball go, if you're playing water polo or something, then the ball would eventually stop actually rather quickly because there's big resistance from the water. And you should ask the question, what's going on here? And of course, in maybe freshman physics, you learn that if you actually write Newtonian equation of motion, there is a piece that goes proportional to the velocity of the object, and that's what we normally call the friction. And you hear about things like terminal velocity, because if you actually solve this equation, then A is time derivative of the velocity. This is a very simple equation to solve. Then you find that this is actually initial velocity times e to the minus k over m t, right? If you take time derivative, you put this one out of the exponent, multiply with this m, you get k. So that's how you get this solution, which means that the velocity is a function of time times exponentially. But what's going on here, if you think about it, is that when a ball is moving inside a water tank, it is hitting the molecules inside this tank. And when it actually hits one, you let these molecules move all of a sudden. So what is going on in any of these processes that actually have a friction is that you would changing macroscopic motion to many to 10 to the 24 microscopic motions. So that's why when you actually put your hand on a desk and move across it, then of course there is a resistance to move your hand, and your hand eventually starts to feel warm. And feeling warm means the molecules in your hand are moving more rapidly, right? Because that's what the heat is. When temperature is high, microscopic objects are moving with higher velocities. So what's going on here in any of these dissipative process, where you're losing energy of the macroscopic motion to many microscopic motions, and that's how you actually lose the energy, and that's the friction. So when you talk about the question, if you have a system with no viscosity, no dissipation, no friction, then you have to understand what's going on with these microscopic excitations. So that's why we like to talk about what are the microscopic excitations based on this quantum field theory, and ask the question under what circumstances you are guaranteed that you're not going to lose the motion of the macroscopic system into many microscopic excitations. So that's why we like to talk about excitations of this system and understand what the prediction would be based on this QFT on microscopic excitation. And it turns out that there's a very simple criteria when you can or you cannot lose the energy of the macroscopic motion into a bunch of microscopic excitations. And that is what is called the Landau criteria. So that's what we like to discuss now. Any questions about where we're going? I hope that addresses the question you're asking. No questions? Okay. So there are two ways to answer this question. One way is to rely on this idea that you can treat DEC as if it were a classical field theory. So what we discussed,
Thank you so much.
here we go, is that this field being this mu over L lambda times some phase is a solution to the classical field theory, and you perturb this solution by a small amount and look at the field equation based on the idea of linearization. The idea is that you first start with the field equation, which is non-linear because of this last term. You can't solve this equation in general, but now you have the solution. You perturb it around the solution and look at only the first order in this perturbation assuming that this perturbation is small, because we are talking about its microscopic excitations, and they solve the equation only to the first order in this perturbation. And that is the process for the linearization. And if you haven't seen this before, then this is actually something we do all the time. When you have seen this idea that LIGO had detected the merger of the gravitational wave coming from the merger of two black holes, that is the linearization on top of the Schwarzschild solution of the black holes, and you actually perturb it around it, and solve for this linear deviation from the sort of exact solution you already have, and that's pretty much all you can do. And when you go to nonlinear, that becomes very difficult, and you have to resort to some heavy weight numerical simulations. But most of the time, we only look at this linear deviation, because when the gravitational wave came to a planet, we actually did this motion. And that happens in when was that? 1915, September 14, when the first gravitational was detected by LIGO. And the entire planet did this, because the gravitational wave is a wave of stretching and shrinking the space and time. Your body did the same thing. And have you ever felt that? Tell me. Nobody? Okay, you guys are serious buddy. So the amount of the stretching that happened on the entire planet was only like 10 to the minus 13 centimeters out of 12,000 kilometers of the diameter of the planet. So it was really, really tiny. And when you have a situation like that, of course, looking at the deviation only to the linear order is an excellent approximation, right? So that's something we do all the time in physics. When you are looking at only tiny deviation from the exact solution you already got, then you are going to linearize your equation of motion and solve it only to the linear order, and that is meant to be an excellent approximation to your problem. So that's one way of approaching this problem. The other way is the operator language. Namely that we know psi of x is an operator. And this gives you the Hamiltonian and once again, you expand this Hamiltonian in creationization operator to the quadratic order, the creation annihilation operator, and when you think about quadratic order, that's something you know how to deal with, because harmonic oscillator is quadratic in X and P. It turns out that when you do the expansion around your solution, then you have a term where you replace both annihilation operators by your solution, and it expanded the quadratic order now has two powers in creation operators. Or you can do it the other way. Now you have replaced these creation operators by your fusion, but now your Hamiltonian has two powers in annihilation operator. So you're looking at an operator, Hamiltonian, that looks like not just A dagger A, but also AA and A dagger A dagger. That looks like a very unusual Hamiltonian, but it turns out that, again, up to the quadratic order, you can solve for this Hamiltonian exactly using a transformation called Bogoliubov transformation. That allows you to solve this real Hamiltonian exactly. So that's another way of dealing with excitations. It turns out that they give you exactly the same answer. And if you learn that dealing with the classical field equation to the linear order, or operators up to the quadratic order, will give you identical answers, which one would you choose? So let me see you raising your hands. Who would choose the classical analysis? Who would choose the quantum analysis? Okay, so we will do both. But I can tell you and assure you, as many of you guessed, this is the way easier than that one. So let's see how that goes. So we first do this one and get the prediction on what excitation spectrum would be. Then understand why there is no viscosity in the Bose-Einstein condensate. And then go back and briefly talk about operator language, which turns out to be a lot more complicated. So let's first do this, and then move to that one later. Okay, any questions here? Yes?
It's not quite obvious to me how we should define mu, the chemical potential here.
Well, chemical potential. So we always assume the chemical potential is positive. Otherwise, this solution didn't exist. So if chemical potential was negative, the only solution we have gotten was sort of the boring one, that there are no particles at all. So we have been assuming that chemical potential is positive, that we have this interesting solution to deal with. Does that answer your question?
Yeah, I guess just what is it defined as? Is it, do we use like the statistical mechanics definition for?
Yeah. So from the statistical mechanics point of view, chemical potential is an incentive to keep the particle in the system. Then when you have a system with this repulsive potential, then energy-wise, it's better off not to put particles in the system at all, because they will repel each other. So you need to have a positive incentive to keep the finite density in the system that would require this positive chemical potential. And another way I briefly mentioned, and I didn't actually delve on this because not everybody has statistical mechanics, is that in stat mech, you learn about this Bose-Einstein distribution. That goes like e to the beta energy minus mu minus 1. So that's what we deal with in stat mech. If we haven't seen this, that's totally okay, because we don't actually resort to this. But the idea here is that if E is the kinetic energy of the point particle, and if mu is positive, then you find that there's a finite radius where the kinetic energy equals mu. And inside this radius, this is negative, then the exponential of negative number is less than 1, then the probability becomes negative. And that's a situation that's pretty totally ludicrous. And what's going on here is that inside this radius of small momenta, then you have to occupy these states, quantum states, with the macroscopic number of the atoms. And unless you actually put in this extra information, that there is this repulsive force among them, you don't know how to treat it. So this Bose-Einstein distribution function is based on the idea that every particle is a free particle, but then you have this problem that you don't know what's going on with this low momentum states. But when you actually put in this repulsive force into the question, then you know what's going on. and it turns out that they will form this condensate. And maybe the best way to actually tell you this is that something I intended to talk about later, but I can mention this now. In some systems of the atoms, where you have these repulsive forces, when you apply certain electric field, but when you dial this electric field to some other number, you can turn the repulsive force into an attractive force. So what you can do is an experiment that you first form this polarization condensate with the repulsive potential among them. Then you find a solution that mimics this classical wave. Everything looks okay, but then you turn the knob and change this repulsive force into attractive force. Then what would happen to this blob of atoms in Bose-Einstein condensate is that there is no longer repulsive force to maintain the finite density, because the density was supposed to be this. And some of you are asking a question on this piazza. N in the homework problem is number density, it's not integer. And in the homework problem, I used a different symbol of curly L to indicate integer to avoid the classical notation. So N is a number density, which is given by mu over lambda. And remember, this lambda was meant to give you this repulsive force among particles. But when you change the force from repulsive to attractive, now you see there's a problem, because this actually turns into a negative number. Attractive force means the potential is negative. Then you see there's some problem going on. So it turns out that the problem is something you can predict knowing this field theory Lagrange. If you look at the potential energy piece, we talked about the fact that it actually looks like this. It goes down quadratically because of the positive chemical potential, and it goes up quartically at the large field amplitudes, and that's why you have the stable minimum given by this. But if you change this repulsive potential, which means positive lambda, to an attractive potential, which means negative lambda, then this potential would change to something like that instead. It goes down quadratically because of the positive chemical potential. Then it goes down even more at higher amplitude because of the negative quartic potential. Then what used to be here starts to roll down the hill. And psi would go to infinite, which means the number density goes to infinite. And what that means is that this whole blob of cold atoms would implode to infinite density. And of course, whenever you hear infinity in physics, that's meant to be an approximation of some kind. So it's not going to be really infinite. This is as much as you can pack all the atoms into tiny space. And at small enough distances, there is some resistance to do that. So it's not going to be really infinite. But you can really see this happening in your experiment. You first form BEC, you turn the knob to change the repulsive force into attractive force, and you can see this entire BEC will just collapse. But when it collapses, then atoms start to feel this the repulsive force when they come to really close to each other, and bounces back. And after this implosion, the whole thing then explodes. And that's also what you see in the experiment. Turn the knob, BC would go squish, and boom. And that's what people call Bose-Nova. And some of you probably know that nova is the name of a star that you didn't see before, but somehow appeared all of a sudden. So it's meant to be a new star, hence nova. And one of the novas, or novae, I guess, in Latin, is the supernovae, which happens when you have an old star, which have the pressure to sustain its weight because of a nuclear fusion process going on at the center of the star. But eventually, a star would exhaust all of the nuclear fuel. Hydrogen fuses the helium, helium would fuse the carbon, the silicon, aluminum, eventually up to iron. But iron is the highest element where further fusion would release energy. Beyond that, the Coulomb repulsion among nuclei would win. By trying to fuse them, you actually have to put energy in instead of get energy out. So you can't go beyond iron in this nuclear fusion process in the star. So once all the elements go all the way up to iron, there's no nuclear fusion going on inside the star, hence there's no energy released, and hence no pressure. Then entire star would collapse. And it turns out that the entire star, that like approximately mass of the sun, would collapse all the way down to the size of like 10 kilometers. A teaspoon of such an object would be like I forgot the exact number, like 100 billion tons. So it becomes really, really dense. Entire star becomes a single nucleus. But when stuff starts to fall against this nuclear core, again, it starts to bounce back. And that is what is called a supernova. So if you like stars, and if you like look at the constellation of Orion, you see this shape you're familiar with. This is Betelgeuse. That's something like I forgot, like a 700 light years away. And this is about to explode. So watch the stars every night to make sure they're still there. And it's actually doing something wild. If you actually look at Betelgeuse is close enough that you can even observe the surface of the star. And you can see the stripes on it because it's actually wobbling. And eventually it would go kaboom. And if it does, it's so close and it's become so bright that you're gonna see it during the daylight. During the day, you can see the star. And then after a while, of course, Orion won't look different. And that's what is called a supernova. At the end of the life of some heavy star, it's going to explode and become so bright, a single supernova becomes as bright as an entire galaxy. And so this idea of this name Bogoliubov is meant to mimic the supernova, that it implodes first, exactly like what the star does, then it explodes. And that's what's going to happen with the Bose-Einstein condensate, where the force is now turned to an attractive force. So what's going on here is that this force being repulsive is very important to sustain the finite density. So the positive chemical potential wants to put particles into the system. Positive repulsive force would like to keep the system away from each other. Then you are looking at the point where they balance with each other, and that's where you find the finite density. And that's not something you can capture in the simple statement. It's gone. Oh, sorry. In the simple statement of Bose-Einstein distribution, where you assume that particles are free, then you find this problem that you have this negative probability. And this problem of negative probability is solved by the fact that you put in these interactions among each other. And that positive potential, repulsive interaction is essential to keep the system in a well-defined density. But when you change that, then you have this instability. The system would collapse. So that's the connection to the standard stat mech. I hope I answered your question.
Sorry?
I hope I answered your question.
No, yeah, it was great. Thank you. I was looking at when Beetlejuice is gonna
Right.
explode.
So the simple stat mech can't capture this because it doesn't have interactions in it. And also it's important that interaction is repulsive. When interaction becomes attractive, then you have this instability. So that's the connection to the standard picture in stat mech. Any questions about this?
I do have a question. First of all, is I don't recall if we address whether or not we only consider like group one elements here. Like
Group what element?
like we consider.
Oh, alkali elements.
Yeah. Yeah.
No, it doesn't have to be. It's just that they're easy to control. So I mentioned that there's a way of trapping atoms by having a profile with a magnetic field, because you can use this interaction with the magnetic moment to create a potential to trap all the atoms inside some specified volume. And for this purpose, you need to have the magnetic moment of an atom, which means that you need to have spins of the electrons. And alkali have only one electron as a valence electron, so that's easy to do.
Then
And you can try using different atoms, but just technically more difficult.
Then I do have a question. So you said that we can control the lambda so that we can manipulate like Bogoliubov.
Uh-huh.
So is a group like alkaline metals the most suitable candidate, or what kinds of elements are there that cannot be controlled?
Well, that's something I don't actually know. So you have to ask some experts in atomic physics. So what you need is a system where you can change from this repulsive force to attractive force with a dialing a knob. And this is what's called a Feshbach resonance. If you're interested, you can look that up. So as a function of this external field, you find a situation that force goes from repulsive to attractive, and it's called resonance because it actually doesn't go to zero. It's not that the force goes this, but rather this. The force would become infinitely repulsive, then minute after, you get infinitely attractive. So that's a transition, that's what is called a resonance, instead of just a crossing. And you can look up what atoms actually show this. I don't remember the answer to this question. There are certain atoms which does exhibit this. I understand rubidium is one of them, but I just don't remember what the criteria are for this Feshbach resonance to happen. Okay? Yes?
Yeah, thank you.
Where does the energy come from for the Bogoliubov?
It's just that
Just the
every
turning-
molecule, of course, has some motion here. And they were held apart from each other because of the repulsive force among them.
Oh, yeah, I know.
Oh.
I mean, the original system, they're just, suppose the original system just have a limited amount of energy.
Uh-huh.
And then why does it explode? Like, there is a huge increase in energy.
Because you have changed the repulsive force to attractive force, then potential energy has all of a sudden become negative.
Oh, so you inject from the outside.
That's right. So you can convert the change of the positive potential to negative potential. That difference turns into kinetic energy.
Okay.
And then once they balance, then that is the kinetic energy when that goes into explosion.
Can we think it as that we inject the energy just as the turning point of the resonance? Resonance.
Resonance.
Yeah. I mean, it looks like when we transition across the resonance point,
Uh-huh.
we inject energy into the system.
Yeah, I suppose that's true. So when you're actually going this way,
Mm-hmm.
then the repulsive force is increasing.
Mm.
That means the potential energy is increasing. So dialing knob is actually putting more energy into the
Yeah,
system.
yeah. Okay. Thank you.
And if you actually look at my slides after lecture, you'll find one slide, which is titled Bogoliubov, as I said. And you find a link. And it's actually a movie. And inside this movie, it's really the experimental data that shows how this blob of atoms actually explode. So I really urge you to watch that movie. Okay? Any other questions here? And thank you for the question, by the way. All right, so now back to the question of how to understand the excitation to the system. So all we have to do is something very simple. We have the equation. You perturb it by small deviation from the solution. Then you keep on the linear term in it, and go ahead and solve it. It's a very simple problem. So now I don't need any of this stuff. I just keep this equation. And look at it in linear order. So, by doing this linearization, psi is mu over lambda square root plus delta psi. And the phase factor here doesn't really matter, it turns out, so I'm going to drop it. And this is actually constant. So upon derivatives, they will vanish. So I can simply change this psi to delta psi. Here I have to do a little bit more work. I really have to expand this and see what happens. Mu psi minus lambda psi lambda psi is now mu. So 2 powers of psi here, right? Then I expand. Lowest order is mu lambda q. And this vanishes, right? Because this is mu to the 3/2 over lambda 1/2. This is also mu to 3/2 of the lambda 1/2, so they cancel. And then you look at the linear term, mu times delta psi minus lambda. I have delta psi dagger, this one squared, mu over lambda. And also lambda, and here's the constant. And I look at the cross term. And everything else is high orders in delta, which I ignore. That's the idea of the linearization. Then let's see, what do you find? So mu delta psi minus 2. This becomes mu over lambda, that's cancelled by lambda, so this becomes 2 mu. So minus q delta psi. And here, I have also minus mu delta psi dagger. So that's how you do the linearization. I hope you get the idea, it's very simple. Did I get this right? I didn't write it this way, so I can't cross-check. Minus mu. It looks right to me. Okay, so let me then proceed. So then this term becomes negative mu delta psi minus mu psi dagger. And now we have an equation which depends both on delta psi and delta psi dagger. So I have to separate real part and imaginary part. Then I try not to do the algebra on the blackboard because I am afraid of making mistakes. So what I'm going to do, so this thing is delta psi. This is the real part. This is the imaginary part. And then when I write this out, I find this equation. From here to there, it's just separating the real part and imaginary part of the same equation. Then you can go ahead and solve it, and you find that the solution tells you that frequency, which is given by omega, so the dEt is omega, and minus I spatial derivative is the wave number. When you actually write this equation using these angular frequency and wave vector, that becomes a very simple equation of omega and k. And you have two equations for two unknowns. You have two equations for two unknowns, and one of them is the overall amplitude because it's linear. Then you can solve them and find the relationship between omega and k, and that actually turns out to be this expression. And what you see is actually pretty simple. So h bar omega, of course, in quantum theory, is meant to be the energy of the excitation. H bar k is the momentum of the excitation. So I can change this to p squared. Then you find the following behavior. P, E. So the idea is that when momentum is small compared to chemical potential, you can ignore the second term. Then becomes mu times p squared in the square root. So when you take a square root of p squared, that's linear in p. So it starts linearly with the momentum. But when momentum is large enough, then you can ignore mu instead. Then this is a square root of the kinetic energy twice. just an ordinary kinetic energy, so it goes quadratically with the momentum. The spectrum looks like this. And this is what is called the Bogoliubov spectrum. And it turns out the fact that this actually starts off linear is the reason why there is no viscosity. And I'll come back and talk about this in a moment. But any questions about these steps? I'm not doing all the algebra on Blackboard because I didn't want to. But I hope the idea, I got the idea across. You already have an equation, and you have an exact solution for the ground state. You take a linear deviation away from the ground state, and you keep only the linear term in the equation of motion, and write it out, and then separate the real part, imaginary part, and then write everything in terms of plane wave in the end, that omega is minus I omega t, k is I kx. And using this plane wave, you can work out the relationship between omega, you get from the left-hand side of the equation, to k squared, you get from the right-hand side of the equation. You go ahead and solve this, and you find the solution. And that actually looks something like this. So that's all I did. Any questions about this? Yes?
Why doesn't it rely on lambda? Is it because it's starting from the ground state?
Yeah, that's right. The ground state knew both about mu and lambda. When I actually linearize the equation, lambda all canceled out, and the equation depended only on v. Okay? Any other questions? I saw a hand up over there. No? Somebody raising hand in serious? No? Sure? Okay. So that's what I did. So getting this is actually not difficult at all. If you have a piece of paper, just work out this linearized equation of motion, then you can find this, what is called dispersion relation. The word dispersion relation is a word that would relate the energy to the momentum. If you haven't heard about this before, there's no phrase dispersion relation. It's just a name to understand how energy depends on the momentum. So this Bogoliubov spectrum is an example of dispersion relation. In normal case, you have E equal P squared 2m. That's the normal dispersion relation you have for a non-relativistic particle. And that really corresponds to the case when you set chemical potential to 0, then this is gone, the energy is in the P squared 2m. But now that chemical potential is positive, this dispersion relation starts out linear with momentum. And that's the main difference. And it might look like this is a small change. I don't mean change as money, it's a small change in the system. But it actually turns out to be very important because this is actually the part of the question whether you have dissipation, namely that whether you can change the macroscopic motion into a bunch of microscopic excitations. So let's actually talk about that.
Oh, sorry, sir.
Yes?
I think you mentioned that we're dealing with microscopic motions right now.
Yeah, that's right. So this is actually microscopic because
Then
this
why
delta
does it-
is meant to be tiny.
Okay, but why does the energy doesn't discretize? It isn't discretized? Because I don't know. I think it should be.
So this is meant to be discretized in the sense that for fixed momentum, energy is finite. And you can create microscopic stations as integer multiple of this energy.
Okay.
So you will see the same thing when we actually talk about the electromagnetic field. In the Maxwell equation, you also find this dispersion relation, namely that omega is ck, and if you multiply h bar on it, energy is c times momentum, and that is the dispersion relation for the photon. And then you interpret this result, which you can get from classical Maxwell's equation, in the quantum way, namely that when you have a photon with a fixed momentum, it costs you finite energy, and you can create integer number of photons. They were 1.5 photon, or pi photon. So for fixed momentum, energy is indeed quantized because you can create a photon only in integer multiples.
Okay. Still, what's the actual function of the psi here? Is it the shape of the functional particles, or is the actual wave function?
So in solving this classical fluid equation, you have the constant, and you're looking at a small deviation around it. And this small deviation has wave vector and angular frequency, and they are given by this relationship. And in this classical solution, the amplitude is not quantized. So it looks like that you can have a sort of arbitrary number of this excitation, pi times the excitation, 1.5, 2.3. But it turns out that when you actually solve this equation, you have to be aware that we are doing this semi-classical analysis. It's not meant to be really classical physics. We never set h bar to 0. So whenever you see energy, the energy has to come in integer multiples of them. And the way you can see this from the QFT point of view is that when you do this expansion in delta psi, you also write your Lagrangian in terms of the delta psi. That is a quadratic Lagrangian, which means that basically it looks like a harmonic oscillator. And when you quantize harmonic oscillator, you get these discrete energy levels. And that corresponds to the number of this excitation, which always come in integers. So what I'm trying to tell you here is that this classical analysis is easy to get this Bogoliubov spectrum, but at the end of the day, you have to quantize it. And I will tell you the process for that too. And if you go straight to the operator language, it's already quantized, so that is done. You don't need to do that again. But algebra becomes far more complicated. So in terms of just getting the spectrum, this classical analysis is easy compared to the operator language. But there's still one step to go, namely that after doing this, working out the spectrum, you have another step of quantizing it, which is that you rewrite this delta psi now as an annihilation operator, and then find the Hilbert space for it. And that's something I haven't done yet. But for the purpose of discussing why this becomes a system with no viscosity, then knowing the spectrum is enough. And that's why I like to jump into the discussion first, before telling you how to complete the steps of working out this quantized nature of these excitations. Is that okay?
Thank you, sir. But I just want a quick answer about what the psi means here. The psi you.
Okay. So that's a good question too. So what I'm actually doing is I have this action which is function of psi, and I'm expanding this around this solution to linear order second order and so on. And the linear order is guaranteed to vanish because this is nothing but the Euler-Lagrange equation. The action is stationary with respect to tiny variation. That's the definition of the Euler-Lagrange equation. Now that this solution we have gotten satisfies the equation of motion, this linear order vanishes by definition. Then you find your action is now quadratic in psi, and you ignore higher orders, And something quadratic in psi is, roughly speaking, harmonic oscillator. So you know exactly how to quantize it. We have done this already. And the answer turns out to be that only thing you need to do is first identify the spectrum. And when you do quantization, you make this excitation to individual harmonic oscillators, namely particles, that you can occupy every momentum state in integer multiples. So that turns out to be the answer. I haven't shown this to you, so if you're puzzled, you should be, but this is the process I'm going through. You first with the classical action, and plug in this solution, that's just a constant, that's not interesting. First order vanishes by definition of this being a solution to the equation of motion. Second order is something you keep, but you know how to quantize this because you have done it before. And the higher orders you're ignoring. And the fact that you can ignore higher orders is this validity condition I mentioned last week, that the coupling constant is small enough in certain unit that you can ignore these higher orders at the end of the day. Okay? Yes?
So I have a question. So in quantum mechanics, then we just have energy, the dispersion relation, right?
Uh-huh.
Which is a purely quadratic function.
Right.
E of t, but now we have a
Bogoliubov spectrum.
spectrum. So does it mean that we can see the Bogoliubov spectrum in real
In
life?
experiment, yes. Maybe that's the first thing I should show. And I didn't prepare a handout for this. I hope you can see this. I can pass this out. So the idea is that this is K, so h bar times K is the momentum. And this is the angular frequency, so h bar times that's the energy. And the idea is that you send in a photon gets scattered and come out. Then you know what the initial photon you send in, you know its energy and momentum. You can measure the energy and momentum of the photon that came out. A difference between them tells you what kind of excitation you have created. So you first measure the difference, how much energy of the photon is lost to the system. That's the vertical axis. You measure how much photon momentum changed, and that gives you the horizontal axis. And you plot it for individual data, and that actually gives you this curve. And it may be hard to see, but if you actually blow up this small momentum region, that is linear. And you see a curve that is more or less parabolic. That is the high momentum behavior we just talked about. But there's an offset by mu. That's a dashed line. And the entire curve, this solid curve, is really the expression over here, and all the data points fall onto this curve. So let me pass this out so that you can all see it.
I have a follow-up question. Then I have two. So first of all will be, so we have the straight line part and then we have the parabolic part.
Right.
Where does the threshold stand and how do we determine it?
That's where the p squared 2n is about mu.
Yes, but the thing is, how do we know that these, like only the first, like the, if I say first order approximation is enough for describing the real spectrum? Because you see the curve can be fitted and maybe say, because we now only consider per psi equals square root of mu over
Okay,
lambda.
so you're talking about this validity condition I
Yeah.
mentioned last week,
Yeah.
when the semi-classical analysis is supposed to be good.
Yeah.
So in the case of this, the Bose-Einstein condensate of cold atoms, the approximation is very good, and you're looking actually into the numbers in your homework problem to know that the validity condition is well satisfied.
Okay.
If you go to superfluid liquid helium, it's not good. And as a matter of fact, you don't get the spectrum, you get something that looks like this. That's because the semi-classical analysis is not good for superfluid liquid helium. So when the approximation is supposed to be good, you really do get the spectrum, which you see the experimental data in the handout. When the approximation is not good, you do see deviation from the prediction, which you expect because semi-classical analysis we're doing here is not supposed to be a good approximation anyway.
Okay.
Does that answer your question?
Yes.
Okay.
Thank you.
Okay, so now comes the real the discussion about why does this linear spectrum tells you that there's no viscosity at all. So this is how the argument goes according to the Landau. You can see there are a lot of Russians in here, Bogoliubov and Landau. And the argument is very, very simple. I only need to find a slide for it. Where is that? Here we go. Sorry. So, again, think about the water tank, and some macroscopic object is moving, and let's say the mass of the macroscopic object is capital N. And then you ask the question whether this would create this microscopic excitation as a result. So what that means is that your initial state is this thing moving with some velocity. Your final state, this thing is moving with slightly different velocity together with this microscopic excitation. And then we know energy momentum has to be conserved, so initial energy has to be the same as the final energy of this macroscopic object plus this microscopic object. Momentum of this macroscopic object should equal to the sum of the macroscopic object with a slightly different momentum plus the momentum of this microscopic excitation. So if you can satisfy energy momentum conservation, then you know you can create this microscopic excitation. Then you can lose the motion of the macroscopic object in a water tank into a bunch of the microscopic excitations, and then this object would eventually stop. So if you're swimming, you'll definitely feel the resistance of the water. If you don't score, then you will stop and sink. And that's what's going on. You are creating a bunch of microscopic excitations in water tank. That's why you stop. So here, this is just a condition for that to happen. So what is it? So initial energy is this. That will turn into final energy with the energy plus energy of this microscopic excitation. That's the energy conservation. And momentum is also conserved. And for simplicity, I'm only looking at the one dimensional for now. So everything is along the same axis. So the momentum is the sum of two numbers. This is the initial momentum along this axis. This is the final momentum along the same axis for the macroscopic object, and the momentum of the microscopic excitation. The question is whether you can satisfy both. So this is already sort of a freshman physics problem now, right? So using the second equation, I solve for V prime. I plug that in the first equation. I expand this. And the first thing you notice is that this big kinetic energy of the macroscopic object is common to both sides, so I can scratch that off. On the other hand, this term here is something I can drop because I'm looking at the momentum of the microscopic excitation over the macroscopic mass, so that's practically zero. Then you find that the equation says 0 equals minus Vp plus E. Very simple. Now what does it mean? We have found the spectrum momentum, energy goes linearly and then eventually quadratically. And V is the velocity of the macroscopic object wading through this fluid. And when V is small, if you look for this solution, you draw a straight line. E equals Vp. And this line doesn't cross this spectrum. Therefore, you don't find a solution for it. Again, remember, this P is meant to be momentum of the microscopic excitation. E is the energy of that microscopic excitation. V is the velocity of the macroscopic object moving through the system. And when V is small enough, then this equation tells you it has to be on the straight line. But because E and P is supposed to be on this spectrum, you don't find a solution, except for the origin where you don't lose energy or momentum. So based on this momentum energy conservation, you conclude that this macroscopic object moving through the system cannot create microscopic excitation. So for V less than this slope, which is given by this, so I can work this out. Energy is square root P squared 2 mu. I'm ignoring P squared 2m here, so that this is P times mu over m. And this is actually the sound velocity, because when you see a spectrum, the energy is proportional to momentum, or frequency proportional to the wave vector, that ratio is how fast that wave can propagate through the system. In this case, that's a sound wave. And when the velocity of the macroscopic object is less than the sound velocity, you don't find a solution. Therefore, you can't lose energy of the macroscopic object into microscopic excitations. Hence, no dissipation, and hence no friction, no viscosity. And if you think of changing the reference frame, instead of this macroscopic object moving in the system, and when you change the reference frame, is the macroscopic object sitting and the system flowing through it. But even in this case, physics is the same, no matter what reference frame you take, you still can't create microscopic excitations this flow can stop into a bunch of microscopic excitations. From here to there is just a Galileo boost. Change of the reference frame. So what this argument tells you is that when the velocity of the fluid is less than the sound speed, then you cannot lose energy of the flow into a bunch of microscopic excitations, even if you have this obstruction in the middle of it. And because you can't lose energy to microscopic excitations, this macroscopic flow can stop. And that's the idea of a superfluid. And I announced this, the video from BBC. It's an old video. I couldn't find something actually better, which is more newer. I hope you watched it. And you have seen this weird phenomenon that this superfluid, liquid helium, inside this beaker, with tiny holes at the bottom of the beaker. When the temperature is high, when the liquid helium is still a normal fluid, it just stays in the beaker. But once the temperature goes down and becomes a superfluid, it starts to leak out through these tiny holes. Because tiny hole does not create microscopic excitations, no viscosity, no resistance, and just keep flowing through these the tiny holes. That's the idea of superfluid. So it's based on this very simple idea whether you can lose energy of the macroscopic motion to a bunch of microscopic motions. And this linear spectrum near the origin tells you that you can. But when you go to higher velocity, this straight line now becomes this. Then you can find a solution. Then you can create microscopic excitations as a result. Then you can lose the macroscopic motion. So this is what is called the critical velocity. The critical. So that's the Landau's criteria. So when you find this linear dispersion relation, that's a sign that you have a system with no dissipation, and hence you lose viscosity, dissipation, friction. I think we are raising a hand.
Yes. Is the physical reason of this that basically the quantum energies are like too big for the microexcitations to?
You could say that. So if you want to dissipate energy into some finite momentum excitation, then energy is too high.
Like the quanta will be too big for the
Right,
microexcitations.
right,
Okay.
right.
Thank you.
You could say that, yeah. Any other questions?
Yeah.
Yes.
Here we only consider the process that only one photon is created. But there's other processes like in the COM frame, there's two photons created with the opposite momentum, and that process is okay.
Yeah, so that's an excellent question. So indeed, so this criteria is probably too simple-minded. And when you apply this criteria to liquid helium, which is definitely more complicated because it's the spectrum, but certainly you can apply the same criteria. So even if your spectrum looks like this, you can still draw the line like this and ask the question what the critical velocity is. And you can work this out. In the case of liquid helium, what you do is the neutron scattering. You have this the liquid helium in your beaker. You send in very slow neutron, typically from nuclear reactors, and then see how that scatters. Again, you know what the momentum energy of the initial neutron. You measure the energy momentum of the final neutron, take the difference, that tells you the excitation spectrum. Then you can plot this, draw the straight line, and work out the critical velocity. But the real critical velocity is much smaller than that. So you're right, this picture is idealized. But this, going from here to there, you have to create multiple excitations, as you said. that will require more complicated setup. When the interaction is weak, that's the case of this cold atom BEC, then probability of creating multiple excitation is very, very low, so that it doesn't really happen. On the other hand, in the case of liquid helium, this validity condition for weak interaction is not true, so you do have this multiple phonon created in the system, and as a result, critical velocity turns out to be much lower. But the fact that for low enough velocity, you still have no dissipation remains true, and therefore the liquid helium does become superfluid, as I hope you watched in the video. Okay, that's an excellent question. Any other questions here? And you mentioned phonon before I mentioned it. So this linear spectrum is called phonon because it is the quantum of sound. And if you go back to the equation we just worked out, you're looking at this linear deviation from constant. And remember, psi of psi was supposed to be density. So if you take the absolute square to linear order, density is now varying. That's what I meant to depict over here. And when you have the varying density of compression and expansion, that's nothing but sound. That's why you can hear me now, right? The air is getting compressed and stretched as the voice of my speaking would propagate into your eardrum. And that's exactly what's going on here. So that's why this can be interpreted as a sound wave, and that's why we call this excitation a phonon. So thank you for mentioning that. Any questions about this? I think the time is up. So I hope at least I convey the idea that you can have this weird system with no dissipation, no viscosity, based on this very simple idea of transferring macroscopic energy into microscopic energy. Okay, and please attend the discussion section tomorrow, because I asked the TAs to talk about this validity condition of the semi-classical analysis, which is beyond the scope of this course, but for those of you who have some familiarity with WKB, you have integral. I hope that will make sense. All right.